Hi everyone, welcome to Dr. G's What the F Prime lecture series on mathematics and physics. And today we're going to be taking a little excursion into what we call integration by parts. Some of you would have seen this in additional mathematics, whatever that means, or you would have seen it in a first year calculus course. Very, very important in applications in terms of physics, engineering, even astrophysics. So you can't really avoid integration by parts. Now the problem is, what most people would call partial integration. But there's a problem because some people view this technique as the differentiation of a product in reverse, and it's not just that, There's something more to this, and that's basically what I want to have a look at before we start getting stuck into problems. So follow closely. All right, so you may have got a glimpse of something on the last slide, something to the effect of u dv is equal to, when I say the integral of u dv is equal to u times v minus the integral of v du. What the hell does this mean? Where do we start with this? How do we interpret this? Has this any connection with anything in calculus? We see these integral signs, we see this minus sign, we're thinking, what's the origin of this beast? Well, let's start with something fundamental. Let's take two functions. We've got a function f of x, and we have another one, g of x. And we're going to assume they smooth, continuous, and well-behaved and differentiable. Now, if we differentiate the product of these, let's see, d dx of f times g, what is that? We apply the product rule from differential calculus, and that becomes, you differentiate f, you keep g constant, then you go plus, you keep f constant, and you differentiate g. Now, if we take the integral on both sides, what do we end up with? So it's integral of d dx of f dot g dx, integrating with respect to x. We integrate both sides, so it's f prime g dx plus the integral of f, what's the next one? G prime dx. Now, what is the integral of the derivative of the product here? Now, we have a look at that very carefully, and that's pretty straightforward. So this really gives us f times g equals to the integral of f prime g dx plus the integral of f g prime dx. Okay, and if we play around with this ever so slightly, we can easily figure this out, and we have something like the integral of, let's just go f g prime dx, which is this guy over here. What is that equal to? That is nothing more than f times g minus the integral of f prime g dx. Now take a look. That's interesting. If we compare what I've just got there, let's call that 1, and what I've just got there 2, and this is exactly the same. So what is this whole procedure trying to tell us? The integration by parts. We have these two functions. We have function f, and in some way there's a product here with this derivative g prime, and we can apply this very simple formula, and out pops the complete integration of this product. So I'm just going to have a look at that very carefully, and then we'll do some examples. Okay, so welcome back, and up to this point, what have I shown you? We had something like the integral of f g prime dx is equal to f times g minus the integral of f prime g dx. Okay, or you can write this in terms of u's and v's. Now the thing is, I've been looking at these formulae, and then I look at examples, and it all comes down to choosing what you want to integrate and what you want to differentiate. So there are simple rules that pop up as we look at each example separately. But I don't want to spend too much time thinking about which function is going to be u and which function is going to be v, and which one do I integrate and which one do I differentiate. We've got to conserve time, we've got to conserve energy and do things in an intelligent, beautiful and elegant way. So over the next 10, 11, 12 examples, hopefully you're going to grasp this technique without dissipating too much of energy in the process. So follow me, and I'm sure you're going to have lots of fun. Okay, so let us start off with this beauty, the integral of ln x dx. Now please do not tell me that the integral of ln x dx is 1 over x. No, please. We've come too far to think about things in that crazy way. So we're looking for a function whose derivative is ln x. So ln x almost looks like on its lonesome self just sitting there in space. But it's not alone. Just like a dark matter candidate in cosmology, what you do have sitting in front of ln x, there's a 1. So ln x is not alone. So here's the big choice. What we really have to do now is to make a choice. Do we integrate 1 and differentiate ln x? Or do we differentiate 1 and integrate ln x? And suddenly you realize, hey, hang on, what am I just saying here now? If I differentiate 1, I'm going to get 0. Right? If I choose to integrate ln x, I'm going nowhere, because that's what the question is asking. So here, we cannot twist you arm. You have no choice. So it's very simple. I have two functions. I'm going to decide which one I'm going to integrate and which one I'm going to differentiate. In this case, there's only one direction. One direction. So we're going to integrate the 1, and we're going to differentiate ln x. So if we apply the rule is very simple. We integrate first and keep the other guy constant. So integral of 1 is x, and we keep ln x constant. Then we have that minus sign. And from the previous slides, we know exactly where that minus sign came from. No mystery there. It's the integral. We carry over what we integrated. There's it over there. And what do you think we do to ln x? We differentiate ln x. And we are integrating with respect to x. Simplify. You have x ln x minus, tidy up here, x dx. Right. No. Over x, because that's x there. So that's really nothing more than x ln x minus the integral of dx, which is pretty straightforward. So what I've just proved is that the integral of ln x dx is given by this very beautiful formula, x ln x minus x plus a constant. Now, if you don't believe that, or if you think I made a mistake, differentiate the right-hand side. So if you take the right-hand side, you take the derivative of the right-hand side, ddx of x ln x, that should be ln x minus 1, and then, ln x minus plus 1, and then ddx of the x is going to be minus 1. The minus 1 and plus 1 cancels out, and exactly what you get is ln x. Of course, the derivative of that constant c is going to be 0. Do that slowly. All right? Some of you are looking at the screen saying, I don't believe this. Well, let's look at the derivative again one more time of the right-hand side. The whole thing. So this is the product. So ddx of x ln x, differentiate x, 1, so it's ln x. Now keep the x constant. ddx of ln x is 1 over x, ddx of minus x is minus 1, plus constant. You don't have to be a rocket scientist or have a PhD in mathematics to see that what I've just done, or what I've just proved right now, is the derivative of the right-hand side equals to ln x Problem solved. Let's move on to the next example. Let's go with something pretty straightforward. You would recall that the integral of e to the x dx is what? Yes, it's e to the x plus a constant. So what would happen if you're faced with something like x e to the x dx? You may try a substitution, and please do not let u equal to x. Oh my goodness. What would happen? So you can try all sorts of things. You can let u equal to e to the x. That's not going to be helpful. And so when these simple substitutions start to fail, then you realize you've got to step up a gear here. And if you look at this very carefully, there's a product. Yes, very interesting. And now you've got to make a choice. And the choice is, which function do you integrate and which function do you differentiate? And one rule that I tend to apply, and that works really well, if you have a polynomial or linear function like x, you don't want to increase the order. What do I mean by that? So I will not choose to integrate x, because if I choose to integrate x, what's going to happen? That's become x squared over 2. And if I differentiate e to the x, of course, the derivative of e to the x is e to the x. So what I would like to do with this e to the x is I would like to differentiate that, because d dx of x is 1, and I choose to integrate e to the x. So that choice is very important. And the moment you choose what you're going to do with one of the functions, then the other one is pretty obvious, right? So I'm going to choose to differentiate x. So automatically I will integrate e to the x. So this integral is very simple, right? So the one I'm integrating first is e to the x, so the x will remain constant. Integral of e to the x is e to the x minus, remember the minus sign, integral. Now, this guy, x, I kept constant. It is now time we differentiate. So d dx of x is 1. And this guy just gets carried over. It's e to the x dx. So that's x e to the x. What is the integral of e to the x dx? It's e to the x plus a constant. So we've just proved that the integral of x e to the x dx is given by the right-hand side. Now, again, having time differentiate the right-hand side, you should end up with the integrand x e to the x as a check. All right. So it's pretty straightforward, you know. Once you get to choose what you're going to do, one of the functions, then it's pretty obvious what's going to happen to the other. Differentiate one, integrate the other. All right, let's move on to another example. Okay, so back, and we're going to look at example 3. You know, you just can't do 2 examples and call yourself an expert in integration by parts. You've got to do lots of them, practice, 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 because every time you open an exam paper, a textbook, a tutorial problem, you're always going to be faced with something new. So the more problems you do, the more familiar you are with the various techniques. Now, you know, it's to give us x e to the x. What about x squared e to the x dx? You take a course in calculus, and then they think you have all the time in the world, and the only thing that you will be doing for the rest of your life is mathematics. Of course, that's not true. So they give you something like x squared e to the x. Now you know exactly what's going to happen here. We've got to make a choice. Remember my little rule, right? In most cases, this works beautifully. Do not increase the order of the polynomial or that linear function. So I cannot choose to integrate x squared, because if I do, I'm going to go x cubed over 3. I'm increasing the order, and that's not pretty. So I'm going to choose to differentiate x squared. And the moment I choose to differentiate x squared, what do you think I'm going to do with e to the x? I shall integrate e to the x. So here we go. We keep the x squared constant. That's what the rule says. We integrate e to the x. We get e to the x minus. We kept x squared constant, so we're going to differentiate that guy, so it becomes 2x. And then we're going to keep this guy as is, e to the x dx. So this becomes x squared e to the x. Now watch this. This is not pretty. X e to the x. We got to integrate again. I'm going to pull that 2 out as a common factor over there. I'm just going to go like this, just to remind us of what we're doing. This is exactly what we did in the last question. So let's just do this for completeness. E to the x minus 2. And watch the use of brackets. So again, I'm going to choose to differentiate x and integrate e to the x. So keep x constant. The integral of e to the x is e to the x minus. Differentiate x, you're going to get 1. Keep this guy constant. You're going to e to the x dx. With me. So this becomes x squared e to the x minus 2 into x e to the x. What is the integral of e? Integral of e to the x is e to the x. And throw in a constant. And then finally what we have x squared e to the x minus 2x e to the x plus 2 e to the x plus a constant. That bracket, if it was not there, it's pretty obvious that you're going to go off by a negative sign, or you're going to go off by some sign in the very final step. So you're going to be very careful and make use of brackets so that the minus sign gets multiplied in the appropriate places. But that's your final answer. So if you want to sharpen up your differentiation, differentiate the right hand side. I challenge you to do that right now, and you would end up with the integrand x squared e to the x. Sweet, simple, straightforward. What happened there? The integral of x ln x dx. What do we do there? So we're going to make a choice. You know, we can integrate x. But I told you earlier, if you integrate x, that becomes x squared over 2. Not nice. And then we choose to differentiate ln x. But that's interesting. Think about this very carefully. And this is one of the exceptions to that rule about not increasing the order. It's because of the derivative of ln x. See, ddx of ln x we know is 1 over x. So if I chose to integrate x, I get x squared over 2. And then I'm going to multiply that by the derivative of ln x, which is 1 over x. And then somehow we're decreasing the order. So let's just do this via 2 methods. And let's see what we get. So get a line straight down this page, down here. So the first one I'm going to do, again, notice I'm not spending too much time thinking about what u is and what v is and what u prime is and v prime. Conserve energy, conserve time. And at my age, where I can see the edge of my grave, I've got to conserve life. So very quickly, I'm going to choose here to integrate x. I'm going to keep the ln x constant in the first move. So if you have a look here, I'm going to choose, let me write that again. It's a beautiful color, by the way. So I'm going to integrate x. That becomes x squared over 2. Keep ln x constant minus. And then I'm going to go in. So it's x squared over 2. That's the guy I'm carrying over. And what is ddx of ln x, which is 1 over x dx. So this becomes x squared over 2. Ln x, just tidy up here, minus a half. And this becomes x integral of x dx. Is that right? Yes, always check. That becomes x squared over 2 ln x. We all know the integral of x. That becomes x squared over 2. And that is finally x squared over 4, because we already have half there. So I've just shown you that the integral of x ln x is given by this very sweet, straightforward, and beautiful. Don't forget the constant there. Now, what if I chose to differentiate x by applying my very simple rule of not trying to increase the order, and I want to integrate ln x? We know the integral of ln x. We proved that. So let's do this. So the integral of x ln x dx, keep x constant, and I've chosen to integrate ln x. From our earlier slide, the integral of ln x is x ln x minus x. It's a beast. Minus the integral. This x, I now got to differentiate that. I get 1. Keep this integral carried over, so it's ln x minus x dx. You can see straight away if you compare the two methods. You see the second one looks rather painful, but anyway, that's x squared ln x minus x squared minus, now watch what happens here. This is cubed. Ln x dx. I'm going to split this up into two integrals. Minus and minus becomes a plus and becomes the integral of x dx. And then we proceed. X squared ln x, don't give up. Minus x ln x, integral of that. And then the last one becomes plus x squared over 2 plus a constant. And having a look at this very carefully and thinking, what's going on? This is what we wanted. There's it on the right-hand side, left-hand side. So what we've got here, let's have a look at this. The integral of x ln x dx is equal to that term, x squared ln x minus x squared and plus x squared is minus x squared over 2. And then you have this guy, minus the integral of ln x dx. Now, it stands to reason, if you think about this, we have this guy and we have an identical bit on the other side. They're both the same. So what if I transpose, bring this guy onto the other side? Then I have two of them. 2 integral of x ln x, so exciting, is equal to x squared ln x minus x squared over 2. And with no stretch of the imagination, oh, I forgot my constant. Whew. That's naughty. Where's my constant? And with no stretch of the imagination, if I divide both sides by 2, check this out. I get exactly what I found earlier. But look at the method in red. Look at the method on the left-hand side. You know, it is so important that you make the right choice. In this case, you know, I still think the version on the right is so much more elegant and beautiful. And you'd say, but well, we're conserving time and life, so I'd go with the left-hand side. So here's the thing, and this is a good point we're going to make, and that is, if you make the wrong choice, then it's going to be very painful. So the only way you can start making the right substitutions and trying to figure out an easy way to the answer is to do lots of problems. Right, so we worked with ln x, the integral of that. We just finished the integral of x ln x dx. How would you cope with one like this? The integral of log of x base 2 dx. What would you do there? So just remember, as we did with ln x is not alone. There's a 1 that resides in dark matter that sits in front of log x base 2. But recall, this is interesting. We can have a change of base here, isn't it? Log of x base 2, what is that equal to? Ln x over ln 2. So check this out. And as an exercise, I'm going to claim the following. So if this log of x base 2 dx is the same as ln x over ln 2 dx, so that is just 1 over ln 2 integral of ln x dx. And guess what? We know the integral of ln x. So we're going to have ln 2. The integral of ln x, remember, is x ln x minus x. Let's just throw in a constant there. So this becomes x ln x over ln 2 minus x over ln 2 plus a constant. Is that going too fast? Not really. Now have a look at this. Ln x over ln 2, what is that equal to? X log x base 2 minus x over ln 2 plus the constant. That's the answer. So if you do that from first principles, You should, if you know what we're going to do is basically we got the 1, we have to integrate it, then we've got to differentiate log x base 2, and I think it's a good idea to actually do that from first principles. You will end up exactly the answer that I received, that I got right over here. So please have a go at that. Beautiful question. One, integral of arc sine of theta d theta. This is going to change the variables from x to theta. You know, we get so used to this thing of x, and then suddenly you put a theta, then people's confused. So how do we integrate this one? What is the integral of arc sine theta? We're looking for a function whose derivative is arc sine theta. That's interesting. Just like with Linux, you would know that there's a 1 sitting in the front. Where does the 1 come from? It's dark energy. So you can't differentiate 1 because d theta of 1 is 0. So we know exactly what we're going to do. We integrate the 1 to give us theta, and you keep arc sine of theta constant minus the integral. The theta gets carried 3 over there. And what is d theta of arc sine of theta? And this is the beauty of mathematics. You can't forget a whole semester, like for instance semester 1, the work that you covered there in Math 1A. You've got to carry through your entire life. Learned for life, not an exam. So d theta of 1 over arc sine theta, if you remember, is 1 minus theta squared d theta. Now this is beautiful. Theta arc sine of theta minus. Now how do we cope with this guy? Theta over the root of 1 minus theta squared. If you have a look at that as an aside, I'm looking at this integral here. If I let u equal to 1 minus theta squared, so you'd end up with du equals to minus 2 theta d theta. It's a substitution. So we let u, and this theta d theta is du over minus 2. So this becomes 1 over root u, which is this guy. Theta d theta is du over minus 2. So we've changed the variables of integration. The minus and minus becomes a plus. Throw in the half there. Integral of u to the minus a half du. Like that. So theta arc sine of theta. What's the integral of u to the minus half du? You throw in the 1, that becomes u to the power plus half, and that becomes 2 over 1, if you remember. And that is nothing more than square root of u. I'll throw in the constant now so I don't forget about it. And your final answer is theta. We've got to go back to the original variables, so that's just 1, and that's going to be root of 1. So we've got that, and root of u should be, because u was 1 minus theta squared plus a constant, and there we have it. So the integral of arc sine theta via integration by parts, very powerful technique, is that over here. Again, I'll challenge you. Differentiate the right-hand side. You should get arc sine theta. All right, so please try that. And some of you would have forgotten your hyperbolic functions and inverse hyperbolic functions, thinking that you'd never see them again and it was all over in the first semester. Guess what? I have a question for you. Integrate arc sine of y dy. And just like arc sine of theta that we dealt with in the last slide, we know that arc sine is never alone. There's a 1 sitting in front. So we know straight away what is the integral of y with respect to 1 with respect to y. So that becomes y. This becomes arc sine of y minus, keep the y constant. So there we are. And so what is d dy of arc sine of y? Yes, you recall is 1 plus y squared dy. So that becomes y arc sine of y, right neatly, minus, now here, have a look at this very carefully. So we're going to have an aside here. I'm going to let u equal to 1 plus y squared, so that du becomes 2y dy. So y dy is du over 2. There's no sign change, the plus sign, so I'll pull the minus sign immediately. So y dy is just du over 2. So I got that, and root of 1 plus y squared is just root u. So pretty y arc sine of y minus a half. I like to write the u as u to the minus a half. And so when I integrate that, I get 2 over 1, and I'll get root u. Throw in the constant before you forget. And eventually, this is looking so red here. Arc sine y 2, so that becomes minus root of 1 plus y squared plus a constant. And there we have it. Easy peasy. Simple, straightforward. And you can do this while watching TV, especially the fashion channel, while you're having supper. Next time you go to a club, share this with the DJ. It's pretty straightforward. Nothing difficult here. So I came across this one. I think it was pretty cool. It's neat. You know, we've been looking at arc sine, and we know at some point we're going to do a u substitution. What if we need to do a substitution right at the beginning? So here's a beautiful example of that. So it's e to the root, not very difficult. So let's go 3s plus 9 ds. Okay, so it's like going like e to the root. So what's the substitution? Let x squared equal to 3s plus 9. So 2x dx is equal to 3 ds. Everyone's happy with that. So this integral transforms to, very simply, 2/3 integral of x e to the x dx. And what happens after that? Well, it's pretty straightforward, right? You get 2/3 integrate by parts. Like I said, let's not increase the power of x, so we choose to differentiate that. So keep x constant, integrate e to the x, we have e to the x minus. Because we kept x constant, we're going to differentiate her, so we're going to get 1, and then we're going to e to the x, just carry that over, dx, and so that becomes 2/3. Love these brackets as well, got to use brackets. Integral of e to the x is e to the x, and we can throw in a constant there if we wanted, and there we have it. Okay, but that's not where we stop. They didn't give us x, they gave us s. So that eventually becomes 2/3. And what is x? Well, x is the root of this guy, so you're going to get root of 3s plus 9. E to the x is e to the root of 3s plus 9 minus e to the root of 3s plus 9, right neatly. And there we have it. Problem solved. Yep. Brilliant. You're really getting the knack of this, and not just wasting energy and time on figuring out which is u, the derivative, nv, and v prime, and all of that stuff. It's pretty straightforward. The moment you choose to integrate one, you automatically got to differentiate the other. Follow the simple rule. Don't forget the minus sign, and also the use of brackets are very important. Now, the next question I like. We've seen this with x ln x, but I thought this is a cute example. E to the theta sine theta d theta. Now, if you have a look at this, e to the theta, I mean, you can differentiate this as many times as you want. And sine theta, you can differentiate, even integrate, right? So here, make a choice. You know, do we integrate e to theta, or do we integrate sine theta? It doesn't really matter. So I'm going to choose to integrate e to the theta, so that becomes e to the theta. Keep your sine theta constant. There's the minus sign. This guy I've already integrated, bring him in there. Sine theta, and I'm going to differentiate. I get cos theta d theta. And so this becomes e to the theta sine theta. What's the bracket? Very important. If you have a look at that, now we've got the product, and I'm going to integrate e to the theta, keep cos theta constant, another minus sign now because this is the second time round we're integrating this thing, or applying integration by parts, and this becomes the integral of e to the theta was just constant, and the derivative of cos theta is minus sine theta d theta. Looks complicated, but it's beautiful, it's elegant, it's straightforward. Well, provided is a minus, minus, minus. Whoa. E to the theta sine theta d theta. So it seemed like we almost stuck in a loop here. Think about that very carefully. What do we have on the left-hand side? We have e to the theta sine theta d theta. So it's almost like a never-ending loop, because there we have this guy, and on the right-hand side we have him again with a minus sign. So if I bring this guy over, I get two of him. E to the theta sine theta d theta must equal to e to the theta sine theta minus e to the theta cos theta. And so eventually what we find, where's my constant? Where did the constant go? Yeah, that's it. It's there. You just can't see it. It's in virtual space. Stephen Hawking would say that. The late Hawking would have said that. Keep your constant there. And so we have e to the theta sine theta d theta. You can just throw in a half, divide by 2, and then you get that guy right neatly. What is this? What is that? Minus e theta cos theta plus c. And that is your answer. You can take out e theta as a common factor, tidy up a bit, but I think what we have done is we applied our rules, our knowledge of this integration process called integration by parts. That's our answer. Pretty straightforward. So what we've done here, if you have a look at this very carefully, we have to integrate twice, and suddenly we see we're in a cycle. If we keep doing this, it's going to continue and continue and continue. So we get to a point where what we're integrating for the left-hand side, we can identify the same thing on the right-hand side. So transpose, that's the word. Take 2 bits of it, divide by 2, and whew, out pops the answer. Beautiful. Time. And this, you might think, but why do we need this? Well, as I said, you'll find this a lot in applications in engineering. Now, some of you have already studied solids of revolution. How do you work this out? You know, the volume of an object. So a typical example here, you've got the curve y equals to e to the minus x. So e to the minus x would go something like that. It cuts there at 1, and we're just going to stop there, x equal to 1. So we're going to take that region over here, and we're going to rotate this region about the y-axis. So we'll rotate about the y-axis, and we use the shell method to work on the volume of that resulting solid. So the integral for that using the shell method is from 0 to 1, definite integral of 2 pi x. Remember, the radius would be x. The function itself, the height of the shell, is e to the minus x dx. So if you have a look very carefully now here, watch, definite integral for the first time. So you use your brackets. X, I'm not going to integrate. I'm not going to increase the order. I'm going to differentiate that. I'm going to integrate e to the minus x. Now watch and pay careful attention. So I keep the x constant, and if I integrate e to the minus x, it's minus e to the minus x. Agreed. And at this point, I repeat, you shall evaluate from 0 to 1. Then continue with the integration process. That's not over yet. From 0 to 1, we kept the x constant. We're now going to differentiate her. So what is d dx of x? It's 1. Minus e to the minus x. That comes over because we've already integrated dx. Watch what I'm doing here. Technique is important. 2 pi, keep the bracket, minus x e to the minus x from 0 to 1. There's a minus sign there, minus and minus, that becomes a plus. And what is the integral of e to the minus x? Well, that's minus e to the minus x from 0 to 1. No constants here. No constant. You know that from Math 1A, we'd call that. And now we start evaluating at the top bound first. So that becomes minus 1 e to the minus 1. Now watch this. Minus and minus becomes a plus. 0 times e to the minus 0. So that goes away. You want to go minus e to the minus 1. And the minus and minus becomes a plus. E to the minus 0 and e to the minus 0. I'm going to repeat this. I'm going to show you this. That e to the minus 0 is not 0. So be very careful over there. And that's your final answer. You can tidy up quite nicely. It's pretty straightforward. That becomes 2 pi minus becomes minus 2 over e. And this is just plus 1. So 2 over e is obviously less than 1. So here we go. That's a positive number. Work on the volume of the solid, and it comes out quite beautifully. So practice this. Definite integrals can be a bit tricky, especially in how you evaluate after integrating. So get practice over that. Okay, so we've come to the end of our little excursion into integration by parts. It's one of the techniques of integration. And I want to leave with a problem that always bothers me, because when I sit down and do it, I never ever get it right at the first time. I always make a little mistake here, a little mistake over there, and eventually get it right. But I'm going to leave this for you, a bit of homework here. It's the integral of sec cubed theta d theta. Have a go at that. It's an interesting problem. A little technique here, a little application over there, trying to recall something or the other, and eventually play around with this thing, and out pops the answer. So hopefully you enjoyed this video, and I'm now off to watch a little bit of fashion TV while you go through these notes and be entertained by my voice. And hopefully at the end of this, as you get to this slide, you would find that integration by parts is a breeze, and that we don't have to be caught up in the world of u, v, u prime, v prime. That's for another dimension. So thank you for listening, and practice, practice, practice.